We'll discuss an example of separable ODE. This example is taken from physics. It is regarding escape velocity. You must be familiar with this concept. We are talking about a projectile of mass m which moves in a direction perpendicular to the surface of the earth. That is, the object is being thrown from the surface of the earth vertically above. If v0 is its initial velocity, we are interested in calculating the height of the projectile reaches. So to do this, we calculate the weight of the object. We know that the weight at any height h from the surface of the earth is given by the formula Wx is equal to the gravitational constant g times the mass of the projectile m, capital M the mass of the earth, divided by r plus x whole square, where r is the radius of the earth. So this will give the weight of the object at height x from the surface of the earth. We also note that the acceleration due to gravity on the surface of the earth, which is denoted by g, is equal to capital G times me divided by r square, where g is the gravitational constant and me is the mass of the earth, r is the radius of the earth. From these two equations, we get that Wx is equal to mg r square divided by r plus x whole square. Can easily calculate this because me is equal to gr square. So this gme can be substituted by small g r square and you get this expression. So here we neglect the force due to air resistance and other celestial bodies. So the equation that describes the motion is the acceleration is minus of this weight, that expression for the weight that we got in the previous slide, this particular expression. Now we'll have a negative sign because it is happening in the opposite direction. You must be familiar with this equation from your physics. Now what we are interested here is about solving this differential equation. So v is the velocity, so v itself is dx by dt, and now this is the expression. The mm can be cancelled, and question is how to solve this differential equation. So here if we replace v by dx by dt, then this will become d2x by dt square, and this whole equation will become a second order differential equation. But we want to solve it as a first order ODE, separable ODE. So we'll see the method. We have an initial condition, namely the velocity at time 0 is v0. So that initial condition is mentioned here. Now using chain rule, we can write dv by dt, that is the acceleration, as dv by dx times dx by dt. And then we know that dx by dt is equal to v. So we can write it as v times dv by dx. So we substitute this quantity here, mm gets cancelled, and we, on the left hand side we write v dv by dx, and that is equal to minus gr square divided by r plus x square. Now this is the variables can be separated here. This is a separable ODE. What do you think? It is linear, nonlinear, or non-linear? It is non-linear because the dependent variable v and its derivative with respect to x, they occur as a product. So whenever such thing happens, we know that it is non-linear. So NL for non-linear. Now we separate the variables and integrate it. So we keep the variable related to v on left hand side. So v dv, and here and dx on the other side with the expression here. Now, after doing that, if we integrate, on the left hand side we have v dv. So integration of v dv is v square by 2. Integration of this quantity on the right hand side is clearly, there is a square appearing here, so its integration will be r g r square divided by r plus x. So it is r plus x raised to minus 2. When you integrate, it will be r plus x raised to minus 1, and this minus sign will go away. So minus r plus x raised to minus 1 means that r plus x is in the denominator, and there will be integration constant. So clearly this is what you obtain after integrating the separable ODE. So here we have a solution of the differential equation, but we have not yet put the initial condition in it. So now we'll put the initial condition on it. We know that the initial condition says that when t is equal to 0, we also know that the x is also equal to 0, because at t equal to 0, the object has not left the surface of the earth. So when t is equal to 0, x is also equal to 0, and at that time the velocity is v0. So when x is equal to 0, when you substitute x is equal to 0 here, we can substitute in place of v0. So it will look like v0 or v0 square by 2 is equal to g r square divided by r plus c. So r and r will cancel. So this is the expression that is here that I was talking about. So from this we can calculate what c is. So c will be equal to v0 square by 2 minus g into r. This we substitute back in this equation and eliminate the constant c to get the following expression. Clearly you can see that this particular quantity, when you substitute it here, so there's a v square by 2 here, there will be v0 square by 2, and so on. So all this you substitute and simplify, you will get this relation. So v will be given by plus minus square root of v0 square minus 2g r plus 2g r square divided by r plus x, the whole square root. Now we are interested in the maximum height that the projectile reaches when it is released from the surface of the earth with a velocity v0. So when x is equal to h, the velocity will be 0, because at the maximum height the velocity of the projectile is 0. So we substitute v on the left hand side to be equal to 0. So we can ignore this square root now, because v is equal to 0. So and the inside expression is written here, and we have replaced the small x by capital H, because we are interested in having the expression when the projectile reaches the maximum height. So this will be the expression. Thus we simplify, keep v0 on one side and the rest of the quantity on the other side. This is how the expression is, and then we can further simplify it to this particular expression. So finally v0 square is equal to 2gr times h by r plus h. Recall that r is the radius of the earth and h is the maximum height that the projectile reaches when released with the inertial velocity of v0. So this is what we were interested in. Now further, this expression is useful in calculating the escape velocity. So how do you calculate the escape velocity? To calculate the escape velocity, we have to let h tends to infinity, that the maximum height it can reach is infinity. So we can take a limit of this as h tends to infinity. So in order to substitute that h tends to infinity, in order to do that limit here, what we do is we divide the numerator and denominator by h. So we will have 1 by r by h plus 1. So when h tends to infinity, we'll have just 1 here, because numerator is 1, denominator is r by h, and h tends to infinity, so that quantity will become 0, and here we have 1. So this whole thing in the bracket after taking limit will be 1. So what we get is the initial velocity v0 square should be equal to 2gr for it to be escape velocity. So any velocity above this quantity, the projectile will escape the Earth's gravity and go into the space. So if we take the square on the other side, we get square root of 2gr. So if you substitute the value of the radius of the Earth and the acceleration due to gravity and calculate this quantity, this comes out to be 11 km per second. Now some more comments about separation of variables. Consider the equation y dash is equal to 3 times y raised to 2 by 3 with the initial condition y0 is equal to 0. So for this particular differential equation, you can clearly see that a function y equal to 0 everywhere on the domain is a solution. Because if it is everywhere 0, that means the constant quantity, so its derivative is 0. So y is equal to 0 on the right hand side and y dash is equal to 0. So it satisfies this differential equation. Y, and also it satisfies the initial condition. So y everywhere 0 is a solution. Now assume that y is not equal to 0. So it is in a variable separable form. We can take this y raised to 2 by 3 in the denominator here and write this as dy by dx, and then you can write this as in this form, dy by y raised to 2 by 3 is equal to 3 times dx from this expression. Now this can be integrated. So when you integrate on the left hand side, what we get is 3 times y raised to 1 by 3, and on the right hand side we get 3x plus a constant. So instead of writing 3x plus a constant, for our simplicity we take that constant to be 3c, and so we can write it in this way: 3 y raised to 1 by 3 is equal to 3 times x plus c, or in other words, y is equal to x plus c cube. So we got one solution here, y is everywhere 0, and other solution is y is equal to x plus c whole cube. Now something strange happens here. We note, before we note that strange phenomenon, first let us note this fact, that if you want the initial condition to satisfy, that is when x is equal to 0, y is equal to 0, we substitute this here, x is equal to 0 and y is equal to 0, we get c is equal to 0. So we get y equal to x cube and y equal to 0 are two solutions of the initial value problem. That means these two solutions satisfy the differential equation as well as the initial condition. Now the interesting fact is that if we construct a function, namely phi k x is equal to 0 from minus infinity to k for some real number k, and x minus k whole cube for all x between k and infinity, then this is also a solution of the differential equation. You can see that this is differentiable. So what I'm talking about is y is equal to phi kx, where phi kx is given by this. Since this is cube is appearing here, this is also a solution of the differential equation. So not only that y0 is a solution, y is equal to x plus c whole cube is a solution, but this also is a solution of the differential equation. And if you want this to satisfy the initial condition, then you just have to assume that k is greater than 0. Then all the solution will also satisfy the initial condition. So that implies what? That the above given initial value problem has infinitely many solutions. So all these infinitely many functions, where k is greater than or equal to 0, are the solutions of the differential equation or initial value problem.